again. We're going to talk about words and morphology. One of the levels of representation that we talked about in the introductory lecture. We're going to talk about this in fairly good detail and about a number of different aspects of this part of language that are relevant to natural language processing. Before that, though, I'd just like to put out a reminder that homework 1 is due at 11:59 tonight, and we'll be releasing homework 2 at the same time, sometime tonight, basically. And homework 2 is hard, and you should start working on it soon, but you have 2 weeks to do it. You have 2 weeks, not because we're nice, because we're not nice. We're awful people. But we don't think you can do it in 1 week. And so we're giving you 2 weeks, 1 week to install OpenFST and 1 week to actually do the work. So get started on it soon. It's something you'll learn a lot from because it's very different from what you're probably used to doing. And stretches different mental muscles and exercises different mental muscles than you're used to exercising. So it's a good exercise, and we encourage you to do it and not to say, I'll drop this one, because you'll need to drop homeworks later in the semester, and then it will be everlastingly too late. So let's talk about linguistic morphology. What is morphology? What is morphology? If you ask a biologist what morphology is, what will they tell you? So it's a study of the structure of organisms, the shapes of things. You know, the structure of things in terms of their physical form. Now, when we're talking about the morphology of words, we're not so much talking about the physical form as we are about the linguistic form, the internal structure that words have. By the way, there's a complaint that a lot of students to this course or courses like it will make, which is roughly the following. They'll say, I'm not a linguist, I'm a computer scientist. Why do you keep talking to me about linguistics? Well, the answer to this is that NLP is not just P. It's also NL. It's also about natural language. And just as you would need to know something about biology in order to do computational biology, you need to know something about natural language in order to be good at NLP, in order to be really good at NLP. So, you know, if you were linguists already, we wouldn't have to talk to you about these things because you would already know them. We're just trying to give you enough background that you can understand issues that relate to NLP and to these linguistic concepts. So what is morphology? Well, it's about the internal structure of words. So that's the first thing to know, that words are not atoms in the sense of Democritus, right? They're not indivisible units. You can divide them into smaller pieces. And if you grow up as a speaker of English or Chinese or a few other languages, this might seem weird to you. Because for the most part, English words and Chinese words are units. They don't have a lot of internal structure. And so you can forget, oh, words in languages are not just atomic units. You can divide them up and talk about what is going on inside of them. But even in Chinese and English, you have examples of morphology. So in English, there's actually quite a bit of morphology compared to Chinese. So you can have words like misunderstandings, where this word consists of 4 meaningful units, maybe 5 if you consider under and stand. I drew that in the wrong place to see if you're watching. If you consider under and stand to be separate meaningful units, then there are actually 5 meaningful units, but there are at least 4. Even in Chinese, which has remarkably little morphology other than what are called compounds, where you take 2 words and put them together to make a bigger word, there's some morphology. So for example, there's this pluralizing suffix, man, that occurs mostly in pronouns like 他们, they, or 我们, us, we, us, but can also occur with some nouns. So you can say things like 同志们 from 同志, which means comrade, and 们, which means plural. Although, as some of you know who speak Chinese and are up on modern lingo, 同志 and 同志们 have come to mean something other than just comrade. So these little units of meaning, these things like man, or understand, or ing, or s, the minimal meaningful units in words are called morphemes. And morphemes come in really 2 types. There are roots, which carry the central meaning of a word, and then there are affixes that you add to words to modify that meaning or to add additional information. And affixes come in 4 types. There are prefixes, like in prenuptial or irregular. There are suffixes, like eyes and or in determinize and iterator. There are infixes. This is not something that you have a lot in English, but it occurs a lot in some languages. But in English, there are some marginal infixes. So for example, you can take the word Pennsylvania, and if you want to refer to it in a deprecatory fashion, you can say, I went all the way to Pennsylvania, and all I got was this in-person experience. So that's infixation. And in a lot of languages, it's not just fun, it's actually really important to the grammar. And then there are circumfixes, which come on where you add a piece to either side of a root or a stem. But not all morphology is about concatenating things, about adding units together. There's also what is called non-concatenative morphology, and we have some of this in English, a general class of non-concatenative morphology that's called apophony that comes in 2 flavors in English called umlaut and ablaut. So umlaut is like changing foot into feet or tooth into teeth to make a plural. And ablaut is where you change the vowel in a verb in order to change the tense and aspect of the verb, or the tense and the form of the verb. But this is small potatoes compared to what happens in Hebrew or Arabic, where they have root and pattern or templatic morphology. And in these languages, roots are kind of like just a sequence of 2 or 3 or 4 consonants. And then you shove vowels into the middle, between these consonants, and lengthen the consonants and do other things to them in order to make new words, new forms of the same word. And then there's infixation, which we've already talked about, which is non-concatenative. So in Tagalog, the national language of the Philippines, then you have an infix you stick into words, and it changes the tense. But this is probably, so all of this is important: roots, affixes, non-concatenative morphology. But what is more important is for NLP is understanding the difference in function between different kinds of morphology. So there is inflectional morphology and there is derivational morphology. And inflectional morphology adds information to a word that is consistent with its context in a sentence. So things like number, singular versus plural, or case, nominative versus accusative, are examples of inflectional morphology, or tense for a verb. Agreement in number, gender. These are all examples of inflectional morphology. They're all about where a word occurs and not about what a word means or what its part of speech is. Derivational morphology, instead of just adding information to words, it derives completely new words, creates new words with new meanings and often new parts of speech. So if you take parse and add an ER to get parser, that's derivation. And if you take repulse and add IVE to it to get repulsive, that's also a derivation. Okay, I just want to stop here and ask if there are any questions so far.
Professor, even though you say in derivational morphology, you create new words with new meanings, I mean, wouldn't you say parse and parser and repulsive have some sort of connection?
Oh, of course. Of course. There is a function from the input to a derivational process and the output. And that's what morphology is all about. So there's a relationship between parse and parser that's similar to the relationship between eat and eater, or between ride and rider, or between, well, any number of other things.
But
Teach and teacher.
It's not as direct as inflectional morphology.
That's correct. That's correct. So it's more, it's less predictable. You know, with inflectional morphology, you're just adding pieces of information. And with derivational morphology, you're transforming a word in some way.
All right. Thank you.
Its form and its meaning.
Yeah. Thank you so much.
You're welcome. Any other questions? So one of the nasty things about morphology, as compared to syntax, is that it's sometimes quite irregular. So you can have formal irregularity. That means that the way you mark something, the way you do morphology, varies depending on what word you're doing it to. So if you compare walk, walked, walked with sing, sang, sung, what you're doing to that verb to inflect it is very different in one case than the other. So this is formal irregularity. There's also, though, semantic irregularity or unpredictability, and this gets to some extent back to the last question. So the same derivational morpheme may have different meanings or functions depending on the base it attaches to. So, by the way, this we have this star here, which I should explain. That means that that's something you can't say. That's a bad piece of language. So you can say a kind old man, and you can say a kindly old man, and you can say a slow old man, but you can't say a slowly old man. So kindly, kind can take li and become an adjective, but slow, when you add li, can only be an adverb, it can't be an adjective. So there's some unpredictability in how li will affect the part of speech of a base that it attaches to. So why do we care about morphology? Well, on the one hand, morphology is a problem, particularly inflectional morphology. So it makes words that are the same word look like different words. It disguises underlying unity in the vest of difference. And so this is a problem for information extraction and information retrieval and various other kinds of NLP tasks, because you end up with some sparsity often in the data, because you're dividing up a single category into a bunch of other categories based on the surface form, and you can't see that those are really should be the same category and should have the same label. So one thing that you need to know about morphology for is getting rid of this surface difference so you can access the underlying unity. But morphology also encodes a lot of useful information that can be useful or in some cases even essential in NLP tasks. This is true in machine translation, in natural language understanding, in semantic role labeling, for many languages. Probably not true for English, where you have massive amounts of data and relatively little morphology. Probably not true for Chinese, where you have massive amounts of data and even less morphology. But it is true for a lot of other languages. In fact, most of the languages of the world are morphologically rich languages, and you have to deal with this kind of problem. And you also have access to this kind of information that can help you to solve problems you wouldn't otherwise be able to solve, because there's this information that's being encoded in the morphology. So in NLP, there are actually pretty good solutions to morphology. There's an old rule-based solution, which we'll talk about today, and which you will talk about on your homework too, which is using finite state methods to do morphology. This is still widely used. So if you go to Google, they actually employ an army of computational linguists to write FSTs to process morphology of every conceivable language. And other companies do a similar thing, because this is a very well understood and very robust technique for handling morphology. But there are other solutions that are now gaining currency. For example, supervised sequence-to-sequence models for morphological transduction, for generation and analysis of morphology, and unsupervised models for morphological segmentation, that is, dividing words up into their constituent morphemes. Let's move to the subject of finite state morphology by way of an introduction to different levels of analysis that you can have of a morphological, of a word, of the morphology of a word. So the form that we're most familiar with is the orthographic form. So things like hugging or panicked or foxes. Often what we want, or what we start with in NLP, is something like a lexical form. This. So we have what's called a lemma, which is sort of like the dictionary form of a word, and then a set of properties, of inflectional properties. So here, as part of speech information, we want to know that it's a verb, and we want it to be progressive. For the case of foxes, we get two different lexical forms corresponding to one orthographic form. It could either be a plural noun or a singular verb. So the problem is, how do we map back and forth between the lexical form and the orthographic form? And one thing that you'll learn is that one way of doing this is having an intermediate form. an intermediate form where all of the morphemes have just one representation each. So in hugging, if we divide it into morphemes, we've got hug with two G's plus ing. What we want in a morphemic form is the rule for when to get rid or add this G, this to double the letter. So we have all kinds of rules that correspond to the spelling rules of English, or all kinds of knowledge that corresponds to those rules that allows us to map between an orthographic form to a morphemic form. And then that makes it easier to go to a lexical form, and vice versa. So we do this, or we can't, one way of doing this, this is not the only way, but one way of doing this is with finite state transducers. These define regular relations, also called rational relations, between strings. Oh. I didn't see some questions in the chat. Let's go back here just a minute. So the caret here means a morpheme boundary, a boundary between morphemes. And the hash mark means word boundary. So that means end of word. So the difference between fox noun plural and fox verb singular, the verb is the one that occurs in sentences like he outfoxes the hounds. And the noun one, fox noun plural, is the one where I found a den of foxes. So they are spelled the same way, pronounced the same way, but they have different, they occur at different places in different sentences. Good questions. So back to FSTs. So they define regular relations, and they're used for a lot of different things in NLP. They have a great property, which is if they're deterministic, and we'll talk a little bit about what that means, then once you compile them, they execute in linear time. So this is much faster than a lot of competing models for doing morphology. This is pretty good. You might think, oh, linear time, why not logarithmic time? But this is actually better than the alternatives. But to understand them, we have to go to something simpler, because this can be hard to get your head around at first. So we have to start with their simpler relative, the finite state automaton or finite state machine. Who here, raise your hand if you have encountered finite state machines or finite state automata before. Raise your hand on Slack, or not Slack, on Zoom. So a lot of you, but not everybody. So by the end of this class, all of you will have encountered them. So finite state automata are formalisms. They're a formalism that has the following um, 5 components. We have Q, which is a finite set of states. And these here, these circles are states. Then they have a special start state, Q0, and a set of final states, F, which is a subset of Q. Then there's a finite alphabet. This brings me to a pet peeve of mine, and that is regarding the word alphabet. So many people, many students nowadays, you young folks, think that a letter is an alphabet. As in, you know, that was an alphabet. A is an alphabet, or B is an alphabet, as opposed to 9 or 8, which are not alphabets. For our purposes, an alphabet is not a letter. An alphabet is a set of symbols, a set of letters. And that's what we mean by sigma, is a set of symbols. They could be any kind of symbols. They don't have to be letters of any language. They could be emojis. They could be completely abstract. They just have to be symbols. And the final thing is you have transitions between these states that have a label S drawn from sigma. And what these do is encode the set of strings that can be recognized by following paths from Q0 to some state in F. So let's look at a concrete example, because that's not very clear. This is a very simple, concrete example. So this is a finite state automaton that generates a sheep language. As you may know, so I grew up around sheep. Sheep are very dumb. They're probably the dumbest creatures that are multicellular. And so they have very simple vocabularies. What are some of the things that are in this sheep language? What are some of the words that could be recognized by this automaton? What about BA? Is that recognized by this automaton? Well, you start here at Q0, and you go B, A. That seems fine so far. What's the problem? It's not an accepting state, right? Q2 is not an accepting state, and we can tell what is an accepting state because it has a double circle. So it has to, Q2 is an end state or an accepting state or an acceptor state, all the same thing. So this, this FSA will not recognize BA. This is out. What about BAA? So Yoshin has the right idea from the chat, and that is you can rewrite this FSA as a regular expression. In fact, you can rewrite any FSA as a regular expression. What is the regular expression that corresponds? There are two different ways of doing it, but what is the regular expression that corresponds to this FSA? So Yoshin says B, A star, exclamation point. That's right. So another way of saying this is B, plus. If you're using like Python style regular expressions and you have a separate plus quantifier. But this is the proper way. So any string that is matched by that regular expression will also be accepted by this FSA. So this would be accepted. This would not. This would not. If you can read that, then you're getting an A for sure. Yeah. So here's something to keep in mind. So people often get confused about this. They get the wrong idea. They get led astray by pedagogy. We tell you to think about FSAs by sort of tracing your way from state to state, consuming symbols from the input state until we reach the final state or accepting state. Then people get confused when you could take more than one transition away from a state. They think, which way does it go? Which way do you go? I don't know. I'm paralyzed by indecision. But that's not the right way to think about it. It's rather better to think about these things in terms of something like depth-first search. So you're going through the whole network, trying to find a path through the network that allows you to start at the initial state, consume the whole string by going across transitions that consume each of the symbols, and that arrive at a final state coincident with the end of the tape. That is, the tape is what the word is written on, and you're moving a pointer across the tape. So don't get confused and don't think, oh, which way does it go for finite state automata or finite state transducers? They can be non-deterministic. And even when they're deterministic, they can they can have what appear to be non-determinisms locally. So something we're going to come back to is the study of formal language, formal languages. So a formal language is a set of strings, typically one that can be generated or recognized by an automaton. So this is pretty different from a natural language, but one thing that NLP people have traditionally done is kind of pretend that natural languages are formal languages. This is less true now than it was at a point in the past, but it's nevertheless true. So there's a set of languages that can be recognized by FSAs, and these are called the regular languages, the same languages that can be described with regular expressions. And it's very convenient that most natural language morphologies belong to the set of regular languages. There's some exceptions, but for the most part, this is true. One thing that you should note is that about regular expressions is that regular expressions in Python or in other modern programming languages are often not regular expressions. They're more powerful than regular expressions, and they can describe languages that are not regular. So can you think of any examples of features that Python regular expressions have that would make them, that would go beyond what you could do with a finite state automaton. So I've got look behind, look ahead, look back. Yeah, back references. You know, this is not something you could do with a finite state automaton. So match groups, also some uses of match groups you couldn't do. You couldn't look ahead, you can't look behind. So here's an FSA for derivational morphology in English. And you know, all this can do is tell you whether a word is a good word or not. And it's very simplified. You know, they used, when this is from your textbook, and when they did this, they took a bunch of transitions for nouns and indicated them as one transition. And in fact, they took all of the transitions that should consist of multiple transitions, one for each symbol, and join them together and treat the whole string as a label rather than treating the individual symbols as labels, which is what you'll have to do on your homework. So FSAs are good at recognizing, but they're not very good at parsing or generating. They're not very good at analysis, and they're not very good at generation. So let's say your input is a word, and your output is a stem or lemma, and the features that are expressed by the morphemes. Ultimately, we don't care about the order that these occur in. We can think of these as a set, but typically we treat them as a sequence, basically in the order in which they appear. So for, let's say we want to map from geese to goose, gooses to goose as a verb, dog to dog as a noun or a verb, leaves to leaf or leaves, leaf as a noun or leave, the singular verb. How could we do this? How could we establish this mapping? Well, we have at least three different options. One option is a table, a trie, and a finite state transducer. Yeah, what is a table? What would the advantages of using a table to do this be, to establish this mapping between orthographic forms and lexical forms? So it would be fast, as Johnson says. You can have constant time lookup. What would disadvantages be? So there's space. You'd have to have a huge table. So there's also the issue of new words. So what happens when you come across a word you haven't seen before? What do you do then? Do you have any recourse? No. There's no handling for what are called out-of-vocabulary items. What about tries? What would the advantage of a try be? Actually, depending on your implementation, try might be worse in every way than a table. But what would a potential advantage of a try be, depending on implementation? A prefix tree. So depending on how you implemented it, it could save some space. You could have a smaller the database could be smaller in size than the table. What disadvantages does it have? Well, similar to a table, you have no way of handling out-of-vocabulary words. You have no way of dealing with words that are not in the lexicon. Finite state transducers give you ways of dealing gracefully with out-of-vocabulary items and using general rules to predict forms, to guess forms, rather than having to rely on knowing the exact mapping all of the time. And you'll learn about this in homework 2. Just had to check when we're ending, since I'm not used to this schedule. So finite state transducers are a lot like finite state automata. They have most of the same components. So, or in fact, they have all of the same components. You just add something. So they have Q, a finite set of states, Q0, special start state, F, set of final states. But instead of having one alphabet, they have two alphabets, two finite alphabets, one for the input side and one for the output side. And then the transitions look like this. We often write them as symbol colon symbol. So there's the input symbol drawn from sigma and the output symbol drawn from delta. So basically, when you go across a transition, then you read the input symbol from the input tape, and you write the output symbol to the output tape. Any questions? So going back a little bit, Mahul asks, could you not update a table with new vocabulary? Imagining a dictionary here. And the answer is yes, but you'd have to do it manually. There's nothing algorithmic that would predict what the forms would be. So I also grew up with cows. They're slightly more, they're more intelligent than sheep, but meaner, actually. The cow is a dangerous beast. And it's possible to translate, as this example shows, between a sheep language to a more sophisticated but equivalent cow language. So if I give this FST the sheep word ba with 3 A's, ba. What does this translate to in cow? Spell it out. So Kratzy's got it, yes. It translates to this. Because we have B to M, A to O, A to O, A to O, and exclamation point to question mark. What if the input is ba with 1 A? What is the output? Rahul says no output. Yoshin says reject. Those are correct. There's no output. It's just rejected because you don't reach an acceptor state. So this is basically how finite state transducers work. This is the basic idea. They can, as I mentioned before, be non-deterministic. So you could have another transition here with the label B goes to N. And then A goes to I. Given such a network, I'll call this Q5. Given such a transducer, what would the output then be for the AAA exclamation point? Well, let's not do that. Let's do BAAA exclamation point. So Justin has the right idea. And while Al Said has it even better. So basically, the output of a finite state transducer is not really a singleton, it's a set. And in this case, both of these outputs would be valid. So why do we care? Well, we care because a lot of languages are sort of like Turkish. We have a Turkish speaker somewhere in this class, right?
Yeah.
Yeah. So could you read this word for us?
So it's uygarlaştıramadıklarımızdanmışsınızcasına.
And how would you translate that? Is this a good translation?
Yeah, as if you're among those, like, I guess it would like be more appropriate to be like those people, because I mean, I guess not those whom we were not able to civilize. Yeah.
So most Turkish words are not this long, don't have this many morphemes. Here you see each of the morphemes here. But some Turkish words have lots of morphemes. And if you look across a corpus of Turkish, a lot of the words are words that you wouldn't find in a dictionary because they're new words that people made up using this machinery, using these morphemes. So you run across these words that would be out of vocabulary pretty often. With an FST, you can encode all of these generalizations, all of these patterns that allow you to build words like this, these massive monster words, and in a relatively compact way. So there are very good FSTs, for example, that exist for Turkish. But this is not a problem just for Turkish. Turkish has a lot of morphology, and can have big words, but it's not the only language that has significant morphology. In fact, most languages, when you move beyond the big five, most languages do have significant morphology. So we can use FSTs to deal with this. Here's some examples from English, which are a little bit contrived because it's English and they're highly simplified. But at the top here in figure 3.3, you have an FSA for English noun inflection. Very simple. You just have pluralization when it's a regular noun. If it's an irregular plural, you have a transition for the irregular plural. It's built in to the FST. And for irregular singulars, it's also built in, hard-coded, basically. We can translate this into an FST in figure 3.13 that actually does analysis. I don't like that slide so much, so I'm going to move past it. So often when you're writing a morphological analyzer for a particular language, you'll divide it into two sections, implementing separate FSTs for morphotactics. This is how you put the morphemes together, and allomorphic or orthographic rules, how the letters or sounds change when you put them next to each other. So morphotactic rules would tell you that you put ing after a root to make a progressive form of a verb or a present participle. But the orthographic rules, the allomorphic rules, would tell you that you double the consonant in beg, for example, that you double consonants before these certain consonants before these suffixes. This is a general rule. And it would be encoded in this other FST. So morphotactics are like mapping between zoch, this is a made-up word, zoch, noun, plural, becomes zoch, plural, zoch, morpheme boundary S. So this corresponds to that, to the S, not the word boundary. So it concatenates the basic forms of morphemes together, concatenates lemmas with affixes, and lemmas in this case can be guessed. So you can have a lemma that you don't know. This is something that will be important to you when you're doing homework too, and that the system guesses. It looks at the word essentially and thinks we could make a full word if the lemma had this form. Then you have the allomorphic words rules that map between the output of morphotactics and surface representation. So these are the rules that map between something like zoch morpheme boundary S and zoches with this E here that didn't occur in the morphemic representation. So this is what is adding the E. So there are two different kinds of information. They're being encoded in two different FSTs, and then as we see, we can put them together. So here's an example of how you might generate inflected forms of English verbs from lemmas. So this is a guesser. So epsilon here, by the way, is the empty string. And this is confusing to a lot of people. What is the empty string? Where is the empty string? So Schonhoff, if that's how you pronounce your name, and Yoshin, basically, so Schonhoff and Mehul Agarwal say basically two quotes next to each other, right? But Yoshin says something important, which is that it's anywhere between symbols. So that's crucial. The anti-string is everywhere. So what this FST does is given any input, and this any here means any symbol to the same symbol. So this is the same as A to A, B to B. And so on. So I'll take any sequence of symbols and map them to either morpheme boundary followed by ING or S or ED. Okay. So if we give it as an input the made up word squig, what would the output be? So Eric Tong says in brackets squig, Yoshin says a very long set. It's actually not very long. So Kevin Robinson has it right. So it's squig, morpheme boundary ING, squig, morpheme boundary S, squig, morpheme boundary ED. So it would be so Mehul says, so here epsilon is just the end of the string. And you can think of it that way. It's at the end of the string. So there's an empty string at the end of any string. And that's the one that you're rewriting as this succession of symbols. So this is morphotactics. Here is orthographic spelling rules. Orthographic rules are spelling rules, which are kind of allomorphic rule. They change the shape of morphemes based on their context. So examples are consonant doubling, like in beg and begging, E deletion, like in make and making, E insertion, like watch and watches, Y replacement, like in try and tries, and K insertion, like in panic and panicked. So all of these are very systematic rules. And you can easily write a rule, an FST, to encode these. And then you can combine those together to make a big FST that implements all of the rules. Here's an example of an FST for one of these rules. You'll actually implement a version of this for homework 2. So this is the E insertion rule. Linguists have a different notation for indicating the same thing, and that is this kind of string rewrite rule. So what this says basically is that the empty string is rewritten as an E in the context where S, X, and Z precede a morpheme boundary preceding the locus, followed by an S and a word boundary. So this underscore here is where the thing that gets replaced is located in the context. This is the left context over here, and this is the right context. So it means the same thing. Yes?
Do you just know where that is based on the morpheme boundary?
Yeah. Yeah. Based on the morpheme boundary and the word boundary, you know that it's the final S. Yeah. So there are a bunch of different FST toolkits, and big companies tend to have their own toolkit, but there are open source ones and free ones like XFST, HFST, FOMA, and so on, that they let you rewrite rules kind of like this and compile them into FSTs. So this is easier than manually constructing FSTs. And you can take cascades of them, compile them into a FST, compose them with other FSTs, and it's very convenient. But that's not what we're having you do for your homework. Because as I mentioned before, we're bad people, and we want you to learn through suffering. No, just kidding. We want you to learn, and we want you to learn the foundations. So here's the interesting thing. If you have a lexicon FST, this is the morphotactic FST. And the allomorphic FST, the orthographic rules. You can join them together. You can feed the input, you can feed the orthographic form into the orthographic rules, then feed the output of that to the morphotactic FST. And you can go the other way too. And this is true because FSTs are invertible. This is something that you'll learn about in more detail in your homework. But basically, you can take an FST and switch the symbols on each transition around, and you get an FST that goes in the opposite direction. So we can take the same FST that we used to take morphemic forms and convert them to orthographic forms and invert it, and we have an FST that will go in the opposite direction. So we can use the same pair of FSTs both to parse and to generate, which is very cool, I think. Well, you can do a lot of things with FSTs. There are a lot of operations that you can perform on them. Composition, concatenation, cleaning closure, union, and kind of intersection. So composition is the most important of these. And this is equivalent, you create a new transducer that's equivalent to taking the output of the first transducer and feeding it as input to the second transducer. That's composition. So you get a completely new FST, a big FST, from combining two smaller FSTs. And the big FST does the combination of the things that the two smaller FSTs do in sequence. It's also concatenation. So this is like you're taking one FST and on it making its final state the initial state of another FST, so that it transduces, well, so if you had a transducer that went from B to A and a transducer that went from C to D, and you concatenated them, then you could have a transducer that went from BC to AD. Reitao Li says, can composition work if T only provides a subset of the input set of S? It still works. It just might reject some cases. You might not, there's some inputs that would be acceptable to that would be acceptable to T, but not to S, and it just rejects them altogether. And then there's Kleene closure. Basically, it's like the Kleene star on operating on transducers. Union, which is important for you. So given transducers T and S, there exists a transducer T union S such that X is in a T union S relation with Y if and only if X is in a T relation with Y, or X is in an S relation with Y. So it's the set. If you imagine relations as sets, and each transducer defines a relation, and union takes the union of those relations, so that if it's okay with either of the transducers, it's okay with the union transducer. Finally, there's intersection, which is very nice. It's like the reverse of union, as you might guess. But FSTs are not closed under intersection. Therefore, OpenFST, which you use in your homework, will not allow you to do intersection on FSTs. So some things that would be nice to do with intersection, you can't do in OpenFST directly. You have to think of another way to do them. This is just the algorithm for composition. Yoshin asks, what does it mean by closed? And what does it mean by closed? Who can tell us? If FSTs are not closed under, intersection, then it means, as Olivia said, that they're not well defined under all inputs. So there are some FSTs, some pairs of FSTs that if you try to intersect them, you get something else other than an FST. So it's not well defined. Yeah, Kratzy Jane has it right. One FST intersected with another won't necessarily be an FST anymore. So people always ask me, by the way, how you do composition of FSTs. And they think it's like some simple thing, like explain to me on the board. Well, actually, there's a fairly complicated algorithm for doing this. Not that complicated, but it's here in case you want to refer to it. This is for weighted FSTs, so it's a little more complicated than for the kind of FSTs we're talking about, but just for your reference. So let's say we have a lexicon FST, this morphotactic FST, and then these allomorphic FSTs. We want to combine everything together into one big FST. So one option, if we're not using OpenFST, is to take and intersect all of these orthographic rules, all of the different spelling rules, and get one FST that recognizes only pairs, only input-output pairs that follow all of the spelling rules. So that's this here. Then we can take the this allomorphic FST and our morphotactic FST, and we can compose them. And then we get one big FST that does all of this stuff. So why might we want to have one big FST instead of passing information back and forth among a bunch of smaller FSTs? So Rahul says encapsulation, and that's basically right. That's one reason. We want to, we don't want to mix things up too much. It's better engineering to encapsulate the whole morphology in one unit that can be treated as a unit rather than be fiddling around with what is inside, to have everything dealt with in a consistent fashion internally. What else? So Sean says you don't have to store intermediate state, and that's also correct. So there's also an efficiency thing, which is that the for a deterministic FST, then the performance, the time complexity is proportional to the length of the input string only. So if you're running the input string through a whole bunch of different FSTs, it's actually less efficient than just doing it through one FST. But even more than that, like for this example, where we assume that you can do intersection, you can't do the equivalent of intersection just by passing inputs and outputs around. Oh, we're over. Okay, let's stop there. We'll post all of the slides. We've gone through the most important part. So look at the slides and make sure you're familiar with them, but we won't hold you too accountable for what is left. Anyway, thank you very much, and sorry for going over. Goodbye.